Now I switch to English. Good morning, everybody. So this is the beginning of part one, as I explained in the last lecture. The course is structured in 4 parts. The first part that we are now going to start is about state model equations for continuous linear systems, although we will speak a little bit about discrete linear systems. And this will be the basis for the second part, which is devoted to state feedback. So you design controllers for linear systems based on state feedback. And then parts 3 and 4 are devoted to nonlinear control based on the concept of state, and also optimal control, which also uses the concept of state. So state is everywhere here. You can, as you can see, the objective is how to write state model equations for different systems. And in my book, it's pages 2763. Okay, you also have some problems there. And I will publish, well, you also have problems published in Phoenix. Okay. So let's review briefly one example that I mentioned in the introductory lecture. And the problem is I have magnetic suspension, very simplified. Okay? So I have a tension U that I can change. This is my control variable. I amplify it, and there is a current that passes through this electromagnetic device, generates a magnetic field that attracts the ball. Now, if I want to write the equations for this ball, let's assume that it moves only up or down in the direction, in the vertical direction. And so I have to define a referential. And I considered some point and upwards. I call this displacement y. So by Newton's law, the mass times the acceleration, assuming that the mass is constant, is the summation of forces applied. Okay? And what are the forces applied? You have electromagnetic force and the force of gravity. So assume that your electromagnetic force is decomposed in 2 parts, one that exactly compensates for the gravity, and the other which is an increment with respect to that. Okay, so I will call U just the incremental part. So I will not write the terms that are cancelled corresponding to the electromagnetic force that compensates the gravity. So my equation is this, okay? And I'm assuming that M is 1, the mass is 1 in some system of units, okay? Now, this is a second order differential equation. Second order, why? Because you see that the highest derivative of y is 2, okay? So this is a second order differential equation. Now, I can define variables corresponding to the position and to the velocity. So I define a variable which is x1, that's the position y, and the velocity x2, and the velocity x2, which is given by y dot. So if I differentiate x1, I get x2 by definition of the variables. If I differentiate x2, I get a second derivative of y, which is u. So I've replaced a second order differential equation by 2 first order differential equations. And these variables are an example of state. So I will later give you a precise definition of state, but essentially it's a set of variables such that you can integrate the equations. Okay. Now let's rewrite this in a different way. So this is a linear system. So I will write it in order to use matrix notation. And I include this matrix here times the vector x1, x2, plus this vector 0, 1, which is times u. Okay. And so I have something which is a vector of derivatives of the state, is a matrix times the state plus a vector times u. Now, what I measure is y. Y is equal to x1. So I write y as a vector times internal product times the vector of state. Okay? So I got two equations. One that relates the forces applied to the system. Forces in this case would be electrical tension, but it's the external stimulus that you apply to the system. And it's a set of first order differential equations. I call it the dynamic equation. And then I have an algebraic relationship between the state and the output. Okay. So usually you can use this notation. You call A this matrix that multiplies the state to get the derivatives, B this matrix, and C this matrix. Okay. So you have a model which is in the standard form x dot equal to ax plus bu, y equals to cx plus du, where in this case d is 0. D is 0. Okay. What is the meaning of d? D means if you have a non-zero d, you have a system in which u directly influences the output. So you have an instantaneous effect of u in y. Suppose that u is a valve position, you open the valve and immediately you have a reaction. Okay. In this case, d is not 0. So what happens is that you change u, and it takes some time for x1 and x2 to change, and then you feel it in epsilon. Okay. So there is a delay. Now, usually you don't have d. So d is usually 0, although not always. Why so? A non-zero d means that you have a system that is able to have an instantaneous action. Usually you need some time. You don't have an infinite power. Although there are systems for which you can have a non-zero d, but you don't have to use an infinite power to mobilize instantaneous y. Okay, there are some algebraic relationships in the variables. For instance, it is possible to write some circuits to illustrate this idea. Now, the other thing is if you have several u's, suppose that you have a system with two inputs, then you would have more columns here. This matrix B is not just 0, 1, but we will have more columns, because if you have, suppose that U has two elements, U1 and U2, then you multiply rows by columns, okay, and you need an extra column here. Also, if you have several measurements y, then you would need more rows in C to generate the different measurements. Okay? There are situations in which you have this. This B matrix is related to the way the actuators affect your system. And the C matrix is related to the way you have placed your sensors. So C is related to the type and position of the sensors, and B is related to the actuators. Okay. Of course, you can have different letters. You can write different letters. This model using different letters, but this is something that in many cases this is the standard notation. For instance, in the book by Franklin and Powell, they call, instead of A and B, they have F and G and so on. And this is H, I think. Well, 90% of the books, they use A, B, C, and D. I remember once I had a Chinese student, and he was coming to me with doubts. And he had a book written on Chinese. Of course, I could not read any word from the Chinese, but there was x dot equal to ax plus bu. You know? So you see the Chinese characters, and then x dot equal ax plus bu. It's a kind of universal language. Okay, so remember this definition of state. It's a set of variables such that if you know them at a certain time, and if the future values of the input variables are also known, then it is possible to compute all the future values of the state by integrating the state equations. Okay? That's the definition of state. In our case, the position and the velocity is a state. Okay? You could say, well, why not add the acceleration? And we discussed that before. Yes, it's a state. The difference is that usually you want to have the least possible number of variables in the state. So by adding the acceleration, you can write equations, but you would not end up with the least possible number of state elements. The state would not be minimum. And an important issue is, when do we have a minimum state? And we will later discuss that. Now, another concept that I want to introduce right now is related to geometric concepts. No? In particular, myself, I'm very visual. I like very much to do plots. So this concept is the concept of state space. In this case, we have two variables. So I put two arrows and I consider this space. So a point means that you have you are at a particular position with a given velocity. Okay, so a point means a specific state, and this is called state space. Okay, and later we are going to develop a number of notions about how the state evolves in state space. For the moment, let's see. Suppose that you have no forces, so u is 0, and I wrote the equations here on the left, you see? What happens? The derivative of x2 is 0, so x2 is constant. Okay, so if you are at this position A, you will be moving. The only possible movements according to the second equation are along an horizontal line. Okay, but now here x1 is positive and x2 is also positive, but in particular x2 is positive, and the derivative of x1 is equal to x2. So x1, since x2 is positive for this particular value of a, this means that x1 has a positive derivative meaning that x1 is increasing. So after a very short time passes, you are going to move to the right. Okay. You could think of what happens when time passes and the state draws a line in state space. Later we will speak about that. Okay, let me give you another element before we move to the next example. Would you like to make some question? Okay, you can interrupt me.
Professor.
Also, because I'm speaking in English, I try to speak in English as close as possible to Portuguese. It's my best Portuguese pronunciation of the English language. But despite of that, or perhaps due to that, sometimes you don't understand me, you just tell me. Okay, if you don't understand me, just tell me.
Professor, in the previous example,
Yes.
We could choose any point of the state, and for example, if we chose a point where the x2 would be negative.
Suppose that you start here. Where are you going to move? Where can you see the hand, the pointer?
Yes.
Suppose that you were here. What happens?
We move maybe to the left because the derivative would be negative, I think.
The derivative of x2 is 0, so it's again an horizontal line, and you move to the left because x1 is negative.
Okay,
that's right. Okay, so if you think of all the possible positions, or at least of many possible positions, probably if you have a positive x2, the lines of evolution of the state are straight lines, horizontal straight lines moving to the right. And if you are in a position where x2 is negative, then the state will evolve according to an horizontal line moving to the left. Okay? These lines are called orbits. Later we are going to speak about it, to refer again to this. Okay? And one interesting thing, which is quite spectacular, is that to know the orbits, you should integrate the equations. Okay, and at this moment, I'm considering that I have an autonomous system, that is to say u is 0, so you only have x not equal to ax. That's the so-called homogeneous equation. And you have to solve it. But what we are going to see is that the solution depends on the eigenvalues and the eigenvectors of matrix A. Have you studied eigenvalues and eigenvectors of matrices?
Yes.
Okay, but you don't remember. But we will come to that again later. And so you compute the eigenvalues and the eigenvectors, and at least in a qualitative way, you will be able to predict whether you are going to have oscillations, or you are going to converge to 0, or you are going to diverge. Okay. Let me ask you one thing. Suppose not in this system. In this system, you can't have any oscillation, no? Either what happens? X1 is increasing or X2 is decreasing. Physically, this is very simple. If you have a ball without any forces, it either falls down, or if you have some initial velocity, it goes up. Okay? Now, remember that you are compensating for the gravity. So you don't have any oscillations here. Our idea of an oscillation in time is something that goes up and down and up and down. What does it correspond here in state space? Can you tell me? What type of curve do I get if I had an oscillation, a periodic oscillation?
We would have a circle.
Not necessarily a circle, could be an ellipsis, depending on the scale of the equations. But it's true. It's something that returns to the same point. So it's a closed curve. Could be a circumference, better to say, or an ellipsis. Later we are going to discuss that. Okay. Okay. So let's move on.
Professor,
Sim?
se fosse assim uma oscilação amortecida, podíamos considerar uma espiral?
If you had a damped oscillation, then it would be a spiral inwards, okay? Let me give you an example. Okay, so let me jump. Probably this slide should be placed before, okay? So in this case, I have this system. In this system, the time solution is a damped oscillation. Don't bother for the moment why how can you get a solution? We will study that later. So you have the time evolution, and at each time you have an x1 and x2 coordinate. I can't remember which one is which, but you have an x1 and an x2 coordinates. So at time t1, you have x1 and x2, these two dots. At time t2, you also have x1 and x2, okay? So you have two coordinates, and now in state space, you mark these points with coordinates x1 and x2. And you see that you start with some initial conditions, 1, 1. So x1 equal to 1, x2 equal to 1. So it's this point here. And then you start having a spiral going, okay, to the origin. Okay, so you have these two representations. One is the evolution of the state in time, the state variables in time. And the other, which is probably new to you, is the evolution of the state, in the state space. Now, I could have started with a different initial condition. It would give me another curve that spirals down. And I could think of all possible initial conditions. So I would have many curves. That's the phase portrait, o retrato de fase, okay? Each of these curves is called an orbit, uma órbita, okay? Now, in 3 dimensions, you also can have it, for instance. This is a funny picture. You have 3 state variables in this system. And you see that you have this spiral that goes down. Okay, this is very easy to find something. Build this example, because you see that x1 and x2 do not depend on x3, and they oscillate with a damped oscillation. The plane x1, x2. If you do the projection in the x1, x2, you would see a projection. And now I have x3 dot equals to minus 0.1 x3. Okay, so what happens? Suppose that x3 dot would be x3. What is the solution of this equation? x3 dot equals to x3. What is the solution? What is the value of x3? What is the function that is equal to its derivative?
An exponential.
It's an exponential, okay? Now, it's an exponential times some constant, okay? And if you have now the equation is slightly modified because you multiply by minus 0.1. So can you see what is the solution? Can you guess what is the solution?
The exponential to the power of -1, 0.1.
Minus 0.1 times t. okay?
Mhm.
Times some constant that corresponds to the initial condition. How could you show, how could you demonstrate, make the proof that this is actually the solution of this equation? What is the meaning of a differential equation? Is a relation between a function and its derivative such that if you put there the function, you get an identity. So what would you do? You guess the x3 is some constant k times the exponential of minus 0.1 times the function x3. How can you prove that this is, times t? So you guess that x3 is minus 0.1 times t. So how can you show that this is actually the solution of this third equation?
We just replace x3 by the function.
And check what?
And just check if the both sides of the equation are equal.
Yes, if you get a true equality, okay? So to verify that a function is a solution of the differential equation, you plug it on the differential equation and you should get a true equality. Everybody understands? No questions? Okay, now let me ask you one thing. Suppose that I wanted from this curve, I would like to have a different curve. What could I do? Another example. So I developed this slide. I think it's a nice slide. I like the picture. And but now I would like to have a different curve in 3 dimensions. Perhaps something that spirals, but not necessarily to the horizontal plane. What could I do? Ideas?
You could alter the x3 function.
I could alter the x3 function, but if I alter just the x3 function, what happens is that it goes slower or faster to 0, or does not go to 0. But suppose that I would like to, instead of, this is a kind of glass, no? There is no basis. It's a kind of glass with no basis. Glass, you see, copo de cocktail, no? Sem base. Suppose that I want to turn it. So I have imagine that this is the axis, which is now the vertical, okay? And you spiral around it. Can you see my pen? Okay, now I want to tilt it and perhaps stretch it a little bit. What could I do?
Include the x3 in the x1 dot and x2 dot functions.
Okay, so mix up things, no? Mix up things. So perhaps what I could do would be, I have a vector, which is x1, x2, and x3, and I would like to have another vector, z1, z2, z3. So in these other coordinates, how can I get systematically one vector from another? I can do it in many ways, but in a linear way, what should I do?
Use a rotation matrix, maybe?
Use a matrix, a rotation in 3 dimensions, for instance. That's good, okay? So I could have a z1, z2, z3, which is some matrix times x1, x2, x3, okay? Now, this looks like a game. Up to now, it was a game. I was speaking about wine glasses, and it's nice to have this curve and so on. Let me tell you something which is more important. So what we are seeing here is that you can generate a different set of coordinates, okay? You don't want the coordinates to collapse, so you don't want Z3 to be always 0, for instance. So what is the condition for that? If you don't want, if you change x1, x2, and x3 into z1, z2, z3 by multiplying by a matrix, so you have a vector z equal to mx. What is the condition on M such that if you have 3 components in X, you also have 3 components in Z? There is a condition on M.
It must be a 3 by 3 matrix.
It must be. What about if it was 0? All the matrix, all the elements of M are 0. What happens to the Z's?
They will be 0 as well.
Okay, so we are mapping all the points of X on 0. Okay, so this is not a good thing. You lose.
It must
you
be a
lose all
non-invertible matrix.
Must be an invertible matrix. Okay, if you want to start with some X and end with a Z with the same dimension, M must be invertible. Okay, so it is square. Okay, but more than square, it must be square and invertible. And for a square matrix to be invertible, you have to ask that the determinant is different from 0. So you could using the rules for derivative, get equations for Z. Later we will see that. But it's not difficult to imagine. I mean, everything that you know now, if I give you the matrix that relates Z with X, okay, you differentiate Z, and since Z depends on X, you get the equations for the derivatives of X, and you put the X's, and then you express them in Z. So you could write equivalent equations on a different set of axes. Okay, can you understand this idea? So you can change your coordinates. And now comes the big important thing, and later we will see this. You can select the coordinates in such a way that some problems become simpler to solve. Okay, so you can say, well, my state variables are physical variables, but then I can change them, and then I use mathematics, and that's it. I lose the physical sense, the physical meaning. I change the coordinates such that some problems become simpler to solve. For instance, designing a controller becomes simpler in the new set of coordinates. And this is a very powerful idea. Okay. Later, we are going to explore this idea. So change your point of view in such a way that your problems become simpler. Okay. There is an historical story, example, very important, related to astronomy. You remember what it is? I'm sure that you have studied that in physics. Changing the point of view made a dramatic simplification on the equations. It was from changing, there was a moment in the history of mankind in which people believed that the Earth was the center of the universe. So the astronomers were describing the movement of the planets and the stars using axes centered on the Earth. And it was very, very complicated. Okay? There was a king of Spain called Afonso the Wise. Okay? And he said that if he had been consulted when God did the world, he would give him a much better solution. So the world would be very simple, because if you put your reference axis on the Earth, then, for instance, there are planets that go forward and then go backwards and then go forward again. So, for instance, Mars, it goes in one direction, then goes back. When you look at successive days, it looks like it goes in one direction, then goes back, and then goes forward again. Okay? This is because the geometry of the planets, they are not ellipses not centered on the Earth, but centered on the Sun. Okay? And there was a big change of coordinate system made by a famous guy who suggested that it was the axis should be placed at the Sun, not at the Earth. Okay? Actually, the word planet comes from wanderer. A palavra planeta vem de, salvo erro, do grego, e significa viajante, porque os planetas andavam para um lado e andavam para o outro, enquanto as estrelas ficavam fixas, porque estão muito longe. Os planetas, havia alguns que pareciam mexer. E o planeta Marte, em particular, andava numa direção, depois andava para trás, depois andava para a frente. Porquê? Porque nós estamos a ver o planeta da Terra, que também está a andar à volta do Sol. Os dois estão a andar à volta do Sol. Se colocarmos um referencial na Terra, todos os movimentos parecem muito mais complicados. Então é muito mais fácil estudar a astronomia, supondo que os eixos estão no Sol, pelo menos a astronomia do sistema solar, do que se estiverem na Terra. Okay? So we have this issue, which is a quite important one, that comes from the geometry approach to state space, which is we can select the state variables such that we can solve the problems in the easiest way. Okay, let's go back. So the point is that if you look, here, if you look here, you can have different coordinates. From U to Y, you have the same behavior, but the state is different, and these matrices become different, of course, and some problems related to design become simpler. Okay? So that's one important thing. We are going to return to this in a more systematic way. Okay, so let me tell you more examples in which, for which you can write equations in the form of a linear state model. Classical example, electrical circuits. I think that you have studied state models for electrical circuits. So the state is usually the tension around, or the tension about the plates of the condensers, and the currents through coils. And the manipulated variables are either current sources or voltage sources. And the outputs can be whatever you want. Either in this case, for instance, the output was the tension drop at this resistor R2. So how can we write these equations? Okay, I'm not going to review the methods for writing the equations of a circuit. You just do a balance. You just apply Kirchhoff's balance of the currents at nodes 1 and 2, and you get these equations. For instance, for node 1, what you have? The current that passes through this capacitor, which is the capacitor coefficient, the capacitance C1, times the derivative of the tension about the capacity, the plates of the capacitor V1, so the derivative. This is the current IC1 must be equal to EU, which is the input, plus the current that comes from V2 to V1, which is minus V1 minus V2 divided by R1, or if you want, V2 minus V1 divided by R1. That's the tension, that the current that comes in this sense from the right to the left, plus U equals to EC1. Okay, so this gives you the first equation. The second equation is obtained in a similar way. Now you can rewrite these equations, divide everything by C1, okay, and you get an A, a B, and a C. C, remember, was V2. So X is X, V1, V2, so it's the second component, C0, 1, to give you the second component of the state, okay? And these matrices depend on C1, C2, R1, and R2, the parameters that define the circuit, okay? Any question? If you feel uncomfortable asking questions in English, ask them in Portuguese. Okay. Now let's see a more complicated example. It's a motor, a DC motor. DC motors appear in many cases in robotics, machines, etc., electromechanical systems. What is a DC motor? A DC motor is with a permanent magnet. You have a stator. You see this green part here. Okay, this has been cut so that you can see the inside. And the stator is fixed. Okay, just a support for the machine, and actually a little bit more than a support, because you have a magnet, a permanent magnet. You see here this green thing. In the scheme, you have this part and this part that corresponds to a magnet. So you have the north pole of the magnet and the south pole of the magnet. So you have a field, a magnetic field in between. And then you have a part that rotates, okay? And this internal part that rotates, it's the rotor. What you have many spirals of copper, okay? So here I have just one spiral. And if you apply a current to each of these spirals of a coil, then what happens? You have a current and you have a magnetic field. So you will have a force, okay? In this direction, the force goes down. In this direction, the current is in the opposite way because it circles, and the force is up. So you will start rotating. You will start rotating, okay? Now, if you rotate, then this current would be pointing in the opposite direction, so you would have an oscillation movement. But what you want to do is a rotation movement. So what you do is you have some metal parts. You see this interrupted circle. And this is made of usually copper. And you have a sliding contact that, due to this interruption, makes that the current always flows in this direction. Okay, this is the so-called collector. Okay, this is the so-called collector. You can see the collector here. Actually, you have many spirals of the coil of the rotor. So you have many pairs of collectors. You have these blades here. You have one blade and the other in the opposite side that are related to this, connected to the same circuit. Okay, and then you have some sliding, usually carbon contact that slides, this is rotating, okay? And when it is rotating, you are inverting the current. So by this simple mean, you ensure that the current goes always in this direction, okay? That's the commutator, okay? The collector, that's the collector. Now, so what is important here? What is important here? We have a spiral of wire that is immersed. From one side, it is immersed in a magnetic field, so you have a force. On the other way, you have this spiral that is moving. It's moving in the magnetic field. So sometimes it's perpendicular to the magnetic fields. Some other times it's tangent to the magnetic field, okay? So since you have a spiral changing, so the flux, the magnetic flux through the area defined by the spiral is different, is changing in time, you will have also a tension here. So if you apply an electrical tension, you force a current, the current is in a magnetic, immersed in a magnetic field, you get a force, this becomes a motor. But the motor is at the same time a generator, okay? This is a little bit difficult to understand, but it's not if you think a little bit. This tension that develops at this terminal actually counteracts the tension applied externally. So that's why you need to beat a resistance. So what are the equations of this story? Okay, so you have an electrical circuit and you represent the electrical circuit. It's a coil, so you assume that it has some resistance R and it has some inductive effect. And then you have this element which represents the collector and the coils. And we have seen that there is some tension at its terminals that counteracts the tension that you apply to the circuit. And then you have a mechanical part, okay? And this mechanical part that rotates is acted by a torque, okay? And you have a rotating mass with some momentum J and perhaps some friction beta. Now, the torque is proportional to the current that you apply, okay? So the current that develops because you are applying some electrical tension here from some batteries. Or imagine that you have a battery here, and if you have a battery here, you induce a current, and the torque will be proportional. This is a constant of proportionality, K, to the current, okay? This proportionality, it depends on the strength of the magnetic field. So I put here this just to remember that we have a magnetic field, although we don't care about this circuit. Now, this counter electromagnetic tension will be proportional to the velocity. The fastest this rotates, omega is the angular velocity. The fastest the system rotates, the biggest will be this E. So there is another coefficient that multiplied by the angular velocity gives you this counter electromagnetic tension. Now, we have these two expressions. One relates the torque, the mechanical torque with the current, another that relates E with the angular velocity. And now we have one electrical circuit. We can write equations for it. And we have a rotating mass, okay? So for the electrical circuit, you just do a balance of tension. So U is equal to what? Is equal to the drop of tension in R, Ri. The drop of tension in L, L di dt. And this counter-electric electromagnetic tension, which is E. But I have an expression for E, remember, E is Kp omega. Okay? And then I have the shaft rotation. Shaft é o veio do motor, a rotação do veio do motor com uma carga mecânica. And the moment of inertia J times the angular acceleration, so the derivative of the angular velocity, is the sum of all the torques. Okay, so you have a motor torque T, and you have an expression for T. T is proportional to the current, minus some friction coefficient times the velocity. So this is the model of the friction force. Now, if you place here the expression for E and here the expression for T, E is expressed in terms of omega, T is expressed in terms of I, you end up with this, and you write equations in matrix form, you end up with this with these state equations. Okay? Questions? No questions? Okay, let me ask you a question. This was, I promise you to have an exercise. So suppose that this is a small servo motor that you want to use in to move the joints of a robot. So you are interested in modeling also the angle, okay? What is the equation that you need to add first? What is the relation between the angular of rotation and the angular velocity? Suppose
the angular velocity is the derivative of the angle.
Okay, let's call theta the angle. So you have another equation, which is d theta dt equal to omega. Everybody agrees? Now, my challenge to you is right now you have three state variables, omega, I, and theta. My voice is finishing. So rewrite these equations in your piece of paper, in a piece of paper, for the case in which you have this enlarged model. So when you have a third state variable, x3 equal to theta, write the equations for this new set of variables. I will give you some minutes for that. And write equations in matrix form, if you don't mind. While you write it, I will connect minha mesa digitalizadora. I can invent a name for that in English. I want to it. Como é que se diz mesa digitalizadora em inglês?
Scanner.
It's not a scanner. A scanner is something in which you scan a picture.
I think it's pen tablet.
Pen tablet, okay, okay. I've learned something. Have you solved the problem I asked you to solve?
Yes.
Okay, so in a moment, I will ask you to give me the equations. Minus K E L So let me change Can you see the whiteboard?
Yes.
Okay. So now I have fazer Deixa para aqui uma atualização qualquer. Estão a ver tudo menos o que eu queria mostrar, não é?
Para nós o ecrã está branco, professor.
Ok. É que eu comecei a escrever. E agora? Não veem nada, não é?
Yes.
Então, espera aí, eu vou fazer aqui uma outra coisa. Quando eu uso a caneta, o tipo abre-me para aqui faz-me para aqui um disparate. Vamos só fazer aqui mais uma tendência. Se não fazemos assim. Eu escrevo sem ser com a pen, escrevo com. Ok, então, eu depois vou ver o que é que se passa com a minha pen e com a minha mesa digitalizadora para resolver isto para aulas futuras. Mas já faço aqui com o rato. Okay, so remember that x3 is now theta. And before we had x1 equal to, conseguem lembrar o ordem?
Omega.
It was omega. Okay, so what shall I write here?
Minus beta over J.
Minus. So what changes? Better to say minus beta. What changes here? This part here.
The last line row.
The last column and the last line. It's, you have to speak a little bit louder. What is your name?
Veronica.
Veronica. Tens que falar bocadinho mais ao pé do microfone.
Okay.
So what changes is just this last line and this last column. So what shall I put here?
All zeros.
0, 0, and here also 0?
Yes.
What about here?
1 and then 0.
And here?
It will be the same as before, and the rest
So
is 0.
0, 1 divided by L. And then here?
0, 2.
0. So, and why so? Why the reason for this one?
Because we know that x1 is omega, and it's the derivative of theta, which is x3.
So this last equation means that the derivative of theta, which is x3 dot, no, it's theta dot, is equal to 1 times x1, which is omega. Everybody agrees? Plus 0, no? Okay?
Yes.
So, okay, this was a very simple exercise. Sorry for taking so long. Any question? And this part of the matrix is the same. It was the old matrix. Now, what about Y? What is the matrix C?
1, 0, 0.
1, 0, 0. And what is the output in this case? Which variable is the output if you write 1, 0, 0?
It will be x1.
And x1 is what?
Is omega.
Omega. So it's the velocity. Now, if you want to have as output, if you measure, the output means the variable that you are measuring. Suppose that you measure the angle. What, and this is multiplied by x1, x2, x3. Suppose that you want to have as output the angle theta. How do you modify this? Veronica, no, you tell me.
We put 0, 0, 1.
0, 0, 1. So okay. Now this is equal to theta. If you measure theta, the y is the variable that you measure, to which you have your sensors attached. Okay. So everybody understood? Any question? Okay, so let's conclude. Let's conclude. And Okay, so to conclude, let me conclude and give you, we still have 10 minutes at least. This is your model, okay? In the linear case, the general linear case, you have x dot equals to ax plus bu, some initial condition, okay, for the state variables, and then you have y equals to cx plus du. In most of the cases, our d will be 0. And also in many cases, you will have m equal to 1. M is the number of inputs. You see, R is assumed to be a vector of then m components. So we have one input, and P is the number of outputs, is one output. But there is one advantage here over, for instance, using transfer function, is that you can describe multivariable systems in a very easy way. Although in most of the course, we are going to consider just one input and one output, so scalar systems. Now, suppose that I want to simulate this, okay? And suppose that I have 3 different types of blocks. I have integrators, I have matrix gains, and I have summation points. How can I represent these equations? Okay. How can I represent these equations? Well, I have an integrator. It seems strange that I don't have a differentiator. Okay. So I use this trick. I have my integrator, and I assume that the output of the integrator is my state variable, my state vector. Okay. So if I have x at the output of an integrator, it's because at the input, I have the derivative of x, because the derivative, when integrated, gives you the variable. Now, I force this x dot to be really the derivative of x. And I know that the derivative of x is ax plus bu. So I pick x, I multiply by a, and I sum here. And sum to what? To b times u, okay? So you have an integrator, you assume that the output is the state, so at input, there should be the derivative, and then you force the derivative to be according to the equation. And y simply pick up x and multiply by c. Any question?
How would it be if we included the d?
Okay, that is you tell me. How would I modify this to have it would be plus du. So y would be cx plus du. What should I do? Perhaps pick up u, and then what should I do?
Pick up.
Multiply it by d.
Multiply by d. So I would need a block to multiply by d, and then
Sum at the end.
Sum at the end. Okay. Good. Let me see. Let me show you. Okay. Before we go on, why to use an integrator and not a derivative? I could place here, instead of buying an integrator, I go to the electronic shop. Instead of buying an integrator, I buy a derivative. Why not to do that? One explanation is because professors are evil. Os professores são maléficos e gostam de complicar as coisas. Qual é a vossa opinião? Claro que não, não é? Digam lá, não, os professores são ótimos. Então, deve haver outra razão. Qual é?
Maybe because you need to define the initial conditions.
Okay, that is a very good point. You need to define the initial conditions. And how do you define the initial condition with the integrator? Is the initial value of the integral. Okay, so in Simulink, for instance, you can cause that to appear. More reasons. Noise. Okay. When I was your age, this was done in electronic means. Now you do it in software, in Simulink. Okay, in Simulink you have a library, and you can represent these circuits. But even in numerical terms, you have numerical noise, so roundups. What happens? A derivative increases the noise, okay? But instead, an integrator decreases the noise, because the integrator, if you go a little bit up or a little bit down, okay, it takes the average. So this is much more insensitive to noise. And there is still a third reason. And this third reason is a pure derivative is impossible to get, because a pure derivative is not causal. It's not obvious, but actually you can show that a derivative, a pure derivative, is non-causal. It's a circuit that whose response depends on the future. Okay, so instead, an iterator is just the area that happened before, the area under the function. So it's causal. Okay, so we prefer, for practical reasons, we prefer integrals, and we do this mechanization. So let me give you just one example. Suppose that you have this state model. So you write the equation separately. You have two state variables, so you need two integrators. So you go to the shelf, can be the Simulink menu, and you pick up two integrators, okay? And you say, well, this integrator has output x1 and this integrator has output x2. So their derivatives are at the input. Now, I write the first equation. I want to force these derivatives to be according to these equations. First equation, very simple. The derivative of x1 is simply x2. So I connect the derivative of x1 to x2, okay? Here on the right. Now, I have to write the third equation and the second equation. The second equation, the derivative of x2 is minus 2x1. So I pick up x1, I multiply by minus 2, and I add here, plus minus 2x2. So I pick up x2, which is here, multiply by minus 2, and I place it there. Plus 3u, so I have some generator here. In Simulink, I would use some source, could be a generator or some block that generates signals. There are several kinds. Multiply by 3 and add here. Now, I want to add the output equation. So y is 4x1 plus 5x2. So I put here a summation point, and then the entries are 4x1 and 5x2. And I have something that represents this equation. If I use Simulink, I could simulate the circuit and get the response. At your times, I would kill someone to get Simulink. I never killed anyone anyway. There was no Simulink at all. And I was doing this electronically. So if you have an electronic integrator, you can write these things like this. Okay? So you could, and the technique would be the same. With an integrator, an amplifiers, integrators, and summation points, you can simulate this linear state model. Any question? Okay, so we stop here. Have a nice weekend. And we will see each other on Wednesday next week, isn't it? Yes. So have a good weekend.
Thank you.
Okay, thank you.
Thank you. Bye-bye.
Bye-bye.
Thank you.
Bye.